Welcome back to the Explainer. We are looking at a truly fascinating turning point in industrial manufacturing today, and I am so excited you're here. We are about to pit a 30-year reigning champion against an absolutely incredible modern challenger. We're talking about the heavy-hitting data, the specs, and the real-world applications of YAG lasers versus modern FSS fiber lasers.
Okay, let's dive into this. For 20 solid years, if you were in the business of toolmaking, medical technology, or precision welding, you used a Flashlamp-pumped Nd laser. I mean, there was virtually no other option. But based on a comprehensive technical analysis by Vision Laser Technique, a massive shift has been happening on the factory floor. So is the old guard finally stepping down? We're going to let the data answer that. Here is our roadmap for today. We'll briefly cover the laser welding evolution, look at YAG versus FSS efficiency, precision and beam quality, maintenance and wear parts, the 3000-watt innovation, and finally, choosing your laser technology. Section 1, the laser welding evolution. Let's set the historical stage here so we can fully appreciate how we arrived at this technological crossroads. So, more than 30 years ago, Nd-YAG lasers were totally revolutionary. Equipped with microscopes, they let engineers repair the tiniest defects in tool and mold making. They dominated the field. But meanwhile, about 15 years ago, in a completely different sector, the telecom industry, scientists were developing laser diodes built for extreme lifespans. Then, in 2012, a company called IPG released the absolute game-changer, the first semiconductor fiber laser modules capable of short pulses in the kilowatt range. Even the established manufacturers realized they had to adapt. Listen to this from Vision Laser Technique. When fiber hit, it was expensive and meant lower profit margins initially, but the writing was on the wall. They knew they couldn't stop the success of this tech, so they leaned in from the start. Section 2. Nd-YAG versus FSS efficiency. This brings us to our first major technical clash, how these two systems actually handle their power consumption. And this brilliantly illustrates the monumental leap forward we're talking about. The traditional Nd-YAG laser operates at an energy efficiency of around 3.5%. FSS fiber, greater than 30%. That is nearly a 10-fold increase in fundamental energy efficiency right out of the gate. But let's take those percentages and translate them into practical reality on the shop floor. For a 600-watt output from an Nd-YAG system, you're going to draw 15,000 watts of heavy industrial three-phase power. Plus, it generates so much heat you need a massive external water cooling system. Now, look at the exact same 600-watt output on FSS fiber. It only draws 2,200 watts. You can plug it directly into a standard 230-volt wall socket, and the cooling is handled entirely by a few basic integrated air fans. The operational footprint is just completely transformed. Section 3, precision and beam quality. Let's shift our focus from the power plug to the actual welding performance, specifically how tight and controlled the laser beam remains. With traditional Nd-YAG lasers, you run into the thermal lens effect. Because of the high thermal load on the crystal, the beam actually gets blurry as you turn up the power, leaving you with a beam parameter product, or BPP, of around 20. FSS fiber doesn't use a thermal crystal like that, so you get zero thermal degradation. The beam stays razor sharp with an incredible BPP of 2.5, even pushed to absolute maximum power. So, the crucial point is what happens when that beam hits your material. Using the exact same 190mm lens, the traditional YAG gives you a minimum spot size of 250 micrometers. The fiber laser pinpoints that energy down to an incredibly tight 100 micrometers. If you're working in microwelding or medical tech, that difference is absolutely everything. Section 4, maintenance and wear parts. Time for round 3. The hidden long-term costs and the inevitable downtime associated with running these machines. Running a traditional Nd-YAG takes constant upkeep. The flash lamps are consumable wear parts. They have to be swapped out 1 or 2 times a year, running you 500 to 1,500 euros a pop. Mirrors and crystals degrade over time. The optical resonator needs delicate manual adjustments every single year. And maybe the most frustrating part? As those flash lamps age, your pulsed energy slowly drops. This creeping power loss forces you to constantly tweak your production settings just to maintain quality. Contrast all of that with the FSS fiber laser. These units are totally hermetically sealed. Zero internal wear parts. No mirrors to adjust, no lamps to swap, no optics to calibrate. Standard maintenance for an FSS laser literally just means taking a cloth and dusting off the cooling vents. That's it.
That's the whole routine.
And the reason they're so indestructible traces back to their origins. The core diode technology was built for telecom, meant to be placed inside signal amplifiers at the absolute bottom of the ocean. A failure down there would be a massive headache and catastrophically expensive to fix, so they had to be virtually bulletproof.
Because of that deep-sea engineering, the diodes inside an FSS fiber laser are rated for an unbelievable 100,000 hours. Think about that. It's roughly 11 straight years of 24/7 continuous operation with zero creeping power loss. That kind of reliability is exactly why Vision confidently offers a 60-month warranty on these systems.
Section 5, the 3,000-watt innovation. If this tech is so great, how are manufacturers actually keeping it affordable for standard shops? Now, what's really interesting here is how companies like Vision bypass the massive six-figure price tag of a true 3,000-watt fiber laser. They use a brilliant engineering workaround. They start with an affordable 300-watt continuous wave fiber laser, build in proprietary heat management technology, and then briefly overdrive those diodes with 10 times their normal current. The result? You get 3,000-watt pulse peaks out of a 300-watt machine. Section 6, choosing your laser technology. We're in the final round. Let's synthesize this technical data into actionable advice for your specific manufacturing setup. So, FSS fiber is the undisputed king of stability. With a tiny plus or minus 1% fluctuation, it's perfect for micromillijoule pulses on incredibly thin wires, and it can be strictly iso-calibrated. The older NDAG fluctuates a bit more, up to 10%, but it still packs a unique brute force punch, delivering massive pulse peak power right out of the gate, even at low average outputs. So, making that final decision, NDAG still totally survives in jewelry making and custom shops. If you have sporadic, low-volume workflows and deal with massive reflective materials like pure copper, silver, or gold, it gives you that raw power with a lower initial investment. But if you are running an automated 24/7 high-volume line in auto manufacturing or medical tech, the stability and radically lower long-term operating costs make FSS fiber the undisputed winner. And that wraps up our analysis. The jump from 3.5% efficiency to over 30% is not just an update, it's a total reimagining of what a welding laser can be. So I'll leave you with this. Knowing the hidden costs of maintenance and power, how will you evaluate and future-proof your own production lines based on these massive technological leaps? Thanks so much for joining me on this deep dive, and keep learning.